Since the dawn of humanity, finding the best way to do something with the least resources and time has been a problem crucial to our species' survival. This is optimization, and it may be one of the most important and longest enduring problems in mathematics. Take Grug the caveman, who's hunting woolly mammoths. He lives in the valley, and the mammoths live on the nearby mountain. On his trip to where they live, how much food does he pack? How many weapons does he bring? Does he take his wife with him? Well, how does Greg know the answer to this complex mathematical multivariable optimization problem? Trial and error. For most of human history, trial and error has been the only way to solve these sorts of problems. But luckily for us, we're not Grug. Over the last few hundred years, a number of analytical and geometrical techniques have been developed for solving this sort of problem, and over the course of this video, we will be exploring 5 of these. The aim of the video is to build an intuition surrounding the general principles of optimization. Along the way, we will introduce interesting examples to test the intuition and logic we introduce. This will culminate in a fascinating practical example of multivariable optimization, which real engineers would be required to solve for a multitude of different projects.
Let's define optimization in a more mathematical sense as the act of maximizing or minimizing a mathematical function, representative of some real situation. In discrete optimization, this maximizing or minimizing is done through choosing between multiple distinct alternatives. But in continuous optimization, which will be our primary focus in this video, it is through graphical or algebraic means that the optimal solution is found, since it is impossible to sort through an infinite number of solutions over a continuous interval. The simplest method of mathematical optimization is done by looking at graphs. Take this function, illustrating the relationship between time of day and electricity demand in the UK. You can see that there are local minima, points which have the lowest output value when compared to the points on either side of them, at around 4 AM and 3 PM, and local maxima, which have a greater y value than the points on either side of them, at 9 AM and 7 PM. In cases where real-world data is collected and graphed and the resulting curve is quadratic or almost quadratic in nature, the scenario can be modeled through a quadratic polynomial. Such is the case for this solar generation curve. By modeling it as a quadratic, it allows us to approximate the maximum point through typical methods like completing the square or the formula x is equal to minus b by 2a.
In many practical optimization problems that you might face in your life or work, there are limits to the resources you can allocate in the process of maximizing your gain. As such, the variables you are manipulating can't just have any value. Say you want 10 Lamborghinis and a house, but like most of us, you have a limited amount of money. The money you have is what we call a constraint in optimization. In many situations, these constraints can be expressed as linear equalities of the form ax plus by is greater than equal to c, or ax plus by is less than equal to c. Let us explore a practical problem to demonstrate how these constraints can influence the process of optimization. But first, let us establish some vocabulary. We call what we intend to optimize, that is, maximize or minimize, the objective function, which we can denote as f of x. Variables are things you can control and are inputs into the objective function, which we will call for now x1, x2, x3, and so on. Constraints are functions which constrain the values that f of x1, x2, x3 can take. Let's return to Grug, who faces an optimization problem that he does not have knowledge to solve. Grug is planning on a hunting expedition and wants to maximize the food he gains from the trip to feed his Neolithic village. On his expedition, he can either hunt from the further away and difficult to hunt ancient bison, which offer the most substantial amount of food, or he can hunt the more conveniently located herd, but substantially less meaty Ice Age elk. And if we remember from earlier, maximization is optimization, which tells us food is our objective function. Bison and elk here both act as variables. Grug can change how many of each he hunts, which in turn affects the objective function f. Let's say Grug can get 400 kilograms of meat from a bison and 100 kilograms of meat from an elk. In linear optimization, each variable is given an axis, so let's plot what we know.
For now, we are using some generic constant c in our linear objective function. In reality, c represents the total food Grug receives from hunting both elk and bison. In reality, we aim to find the optimal value of c through the manipulation of the variables.
Now for the constraints. Since the elk are located closer, it takes less walking to find them, but they also provide less food. Bison take longer to find, but provide substantially more food. Let's say the distance traveled to find an elk is 10 kilometers, but it takes 30 kilometers of walking to find a bison. If Grug knows he can only walk for 120 kilometers in a day, we can say that 10L plus 30B is less than equal to 120. Also, in his area, there are only 5 bison and 20 elk. This can also be expressed as inequalities. Based on this, we create a kind of shape within which the ideal solution can exist. Since we know that optimization is in essence a study of extremities, one of the vertices of this polygon will be the maximal solution we are looking for. We can determine this by drawing the line for the objective function. By varying the value of this function, we see that it increases outward from the origin, and when it passes through the vertex 5, 2, it has the greatest value. In this situation, it ends up being best for you to hunt all 5 bison and make up the difference into the time by hunting 2 elk. But let's complicate this a bit by saying that each animal requires some number of arrows to hunt. You have 100 arrows, and each bison takes 30 arrows to kill. The elk are much easier to kill at 5 arrows each. Following the same process, we see a new solution in this case. Hunt 2 bison and 8 elks. From this, you can see how adding constraints changes the value of the optimal solution. Through this example, we can understand a few core principles of optimization. First, the objective function is a relationship we are trying to optimize. Secondly, in real-world scenarios, these objectives are often subject to constraints. And lastly, when dealing with constraints particularly, the optimal point does not have to be a vertex of a curve, and can instead be satisfied by a boundary condition.
Before we move on to the next level, it's necessary to go through some prerequisite information. If you are unfamiliar with the basics of differential calculus, or you need a refresher, I will briefly explain what a derivative is, as well as what it describes. If you have a solid foundation on differentiation, feel free to skip to the timestamp shown on screen now. When you're first introduced to the topic of slopes, you only consider it for linear functions by taking the ratio of how much a function rises to how much a function runs, or a change in y over a change in x. This method falls short when you consider functions with changing gradients, essentially any non-linear function. In this case, when you're asked to take the same ratio, you get an average slope between the 2 points. If instead we wish to calculate the slope at a particular point, we need to introduce the derivative, which is the instantaneous rate of change of one variable with respect to another. Typically, this is the change in y with respect to the change in x. Practically, the derivative is an equation which outputs the slope of a function that is usually either denoted by f dash of x or dy by dx. Let's first consider an example from before the discussion of rates of change and the invention of calculus. This will allow us to understand why derivatives and slopes are essential to finding maximum and minimum points without requiring in-depth knowledge on prerequisite information. When Johannes Kepler was buying wine, he realized that there was a flaw in the method used by the wine merchant to determine the barrel's volume, and therefore decide its price. You see, the merchant would insert a measuring stick into the bunghole of the wine barrel, measuring the diagonal length of the barrel to its edge. The merchant assumed that the greater the diagonal measurement, the greater the maximum capacity of the barrel. Kepler challenged this assumption, realizing that a short, stout wine barrel could have the same diagonal measurement as a long, thin one, while their volumes may differ. This led Kepler to the question, for a fixed diagonal length L, what are the dimensions, the height, and diameter that would give the maximum volume of wine possible? To solve this, Kepler modeled the scenario algebraically, in terms of a single variable. Through the use of Pythagoras' theorem, Kepler related radius, height, and length as follows. Then, by using the standard equation for the volume of a cylinder, V is equal to pi RH, we arrive at the following expression, where L is the diagonal length. For simplicity, we will suppose this equals 1 meter. By using the final function for V of h, Kepler could make small increments in the value of h to find where the output starts to decrease, thus being able to approximate where the maximum volume is. While doing this, he came to a few fundamental conclusions. On either side of the extrema, the slope had opposite signs, leading him to realize that at the extreme point, the slope had to be 0. Since the derivative represents the slope of a function at any given point, we can set the derivative equal to 0 to find all the points on the graph with 0 gradient, in theory revealing to us all the maximum and minimum points on the function. We start by taking the derivative of v of h. This can either be achieved by expanding it out or using product rule. Then, by setting it equal to 0 and solving for h, we get h equals 1.15 meters. Thus, the volume of the wine barrel is maximized when h is equal to 1.15 meters, right? Or is it? Well, we have just established that the graph is at some sort of 0 gradient point when h equals 1.15. This could be a maximum, a minimum, or something else entirely. The point is, we have yet to classify what type of point it is, and for now, we just know that it is a critical point on v of h. To classify it, we need to consider the sign of its derivative, or the shape of the graph. At a maximum point of a function no longer increases. The slope goes from positive to negative, which means in this region, the derivative, in general, is decreasing. Whereas the opposite is true for minimum points. To check how a derivative changes, we must find the derivative of the derivative. This second derivative of the parent function v of h describes the rate of change of the rate of change. If the second derivative is negative at a particular point, this means that the derivative is decreasing at that point, and vice versa. So all we need to do to classify the critical point at h equals 1.15 meters is to take the second derivative of v of h and check the sign at the point. So we start by differentiating v dash of h to get v double dash of h equals negative 3 pi by 2 times h. Then, substituting h equals 1.15 meters, we get v double dash of 1.15 equals negative 5.44. We know now that 1.15 is the maximum volume, as the second derivative is negative at that point. This implies that the slope is going from positive to negative on the graph of v of h, which means that it has to be a maximum value. Now that we've understood the first and second derivative tests, let's apply it to a somewhat more practical example. Let's go back to our friend Grug, who has encountered a situation similar to a very famous problem. Grug, who's currently standing on hard land, is on a hunting expedition when he spots a woolly mammoth resting in the snow some distance away. In between Grug and the woolly mammoth is a boundary between hard land and soft snow. Grug can travel 6 meters per second on land, but only 2 meters per second in the snow. We are meant to find the path that takes Grug the least time to reach the woolly mammoth. This can be better visualized with a coordinate grid. Let's suppose Grug stands at the origin 0, 0, and the snowland boundary is 60 meters away at y equals 60. The woolly mammoth is 80 meters away vertically from the boundary and 120 meters away from Grug horizontally. This places him at the point 120, 140. Now we need a function for the total time which is dependent on where Grug enters the snow. Let's label this point of entry p of x, 60. where x is a horizontal point of entry for grug. We can now use the basic speed-time-distance relationship to form t of x. Now, we can find expressions for land distance and snow distance in terms of x through using Pythagoras' theorem, as follows. Inputting both these expressions back into the function t of x gives us our function to optimize in terms of a single variable, the total time t of x. We have now modeled the situation algebraically. This is the first step and possibly the hardest in every optimization problem. Optimizing should become the easy part, as all we need to do is differentiate and set it equal to 0 and solve for x. Doing so leaves us with x equals 96.395 meters, meaning that is the ideal point of entry for grug. Don't worry if you struggle with the differentiation, as this is the easy skill to learn. Focus on developing the intuition behind solving and forming and modeling these situations algebraically, as that is the truly crucial part of these problems.
In level 3, we saw examples where the objective function had one variable as a parameter, like vh, as well as a limited case with an objective function in 2 variables in linear programming. However, many real-life problems are dependent on many variables. For example, in physics, the drag force on an airplane is dependent on the drag coefficient, which itself is dependent on many factors, as the reference area of the plane, the density of the air it's moving through, and the velocity of the plane relative to the surrounding air, many of which will change during the flight. If we were trying to find the times of maximum and minimum drag throughout a plane's flight, we would need to optimize this multivariate function. The methods to do so are similar, yet slightly more complicated than in optimizing single variable functions. First, let's consider what optimization would look like graphically. Let's say we have a simple objective function, f of xy, which, as you can see, has a maximum here. As previously explored for single variable functions, through the process of optimization, we seek to find a minimum or maximum of a function, which occurs when the gradient of the function is 0. However, we need to consider functions differently for multivariable functions compared to single variable ones. To demonstrate, imagine you are walking up a hilly path in the mountains. At a particular part in your walk, in the direction you are facing, it is very steep. However, because the path has been leveled, it is flat to the left and right of you. This illustrates the problem with using a linear definition of gradient when considering multivariable functions. The slope in the x direction and in the y direction may be different. We must therefore introduce a new way to find and combine both of these directions of slope. Let's look again at f of xy. At some point x0, y0, we wish to determine what the instantaneous gradient is in both the x and y directions. We can find the gradient in the x direction by setting y as constant. What this does is it takes a slice of the function at z is equal to y0, resulting in a curve in terms of x. We can differentiate this curve as we did in level 3. However, we need a new notation for this kind of derivative. Mathematicians call it a partial derivative because it's the derivative of part of the function with only respect to one variable. We can follow the exact same process to determine the partial derivative for f of xy with respect to y. To express our results as one mathematical object, we can package both of these derivatives into a vector, which incidentally points in the direction of the steepest ascent or descent. We can use this mathematical definition of multivariable gradient to define maxima and minima for the sort of function that we're exploring. Just as how stationary points for single variable functions are defined as occurring when the gradient is 0, we can define our stationary points for f of xy as when the multivariate gradient is equal to the 0 vector. That is, when each partial derivative that makes up the vector is equal to 0. In the case of f of xy, we can see that this point occurs at 0, 0, 3, which agrees with what we see in the graph. Now let's briefly discuss multivariate gradients in more detail, particularly their direction. Since we are organizing the two partial derivatives as a vector, and vectors have both magnitude and direction, the gradient must point somewhere. When we add together the x and y components of the gradient at a particular point, we find that the gradient vector points in the direction of the steepest ascent or descent. When viewed on a contour plot, which is like a topographical map of the function, this results in the gradient vector at a particular point being perpendicular to the level curves, or lines which indicate a constant z-value. This representation and understanding of multivariate gradient will become important in level 5, so keep it in mind. So now we know how to find places on the function where a gradient is equal to 0. From working in the 2D plane, we know that these points can be either maxima or minima. However, a third class of points, where the gradient is 0, emerges in 3 dimensions. This point is called a saddle point, since it looks a bit like a horse saddle. Despite having a flat gradient, it is neither a minimum nor a maximum. This means that in optimization, it is important to be able to recognize this type of point. However, it is not possible to distinguish between minima, saddle points, and maxima using the first derivative alone. We need something similar to the second derivative test used to determine the concavity of a function that we explored in level 3. Let's explore the 3 types of points we see in this new function, g of x and y, through their first and second partial derivatives at different stationary points. We take a second partial derivative by taking the first partial derivative again. In this case, let's look at the first partial derivatives first. We follow the same process discussed previously, yielding the equations shown. But we see that both the derivative of g with respect to x and the derivative of g with respect to y are functions in terms of both x and y. This implies that when we take the partial derivatives of these partial derivatives, we must also take them both with respect to x and to y. As such, our second partial derivatives are the second partial derivative of g with respect to x and x again, the second partial derivative of g with respect to y and y again, and the second partial derivative of g with respect to x and to y. By setting the first partial derivative of g with respect to x and the first partial derivative of g with respect to y to 0 and solving simultaneously, we find stationary points at a number of points. From our graph, we know that 2 of these are maxima or minima, and if we look at the table of points and their different second derivatives, we notice that for the maximum, both the second derivative with respect to x and the second derivative with respect to y are negative. Like in single variable calculus, this indicates that a local maximum is present. For the local minimum, the opposite is true. Both of these double derivatives are positive. We notice that the mixed double derivative with respect to x and y both is equal to 0, but I will caution that this isn't always the case. For saddle points, on the other hand, we notice that the pure double derivatives with respect to x and y are equal to 0. This indicates that something analogous to a turning point in single variable calculus is happening here. However, I also will caution that saddle points are also possible when one of these derivatives is positive and the other negative for the same point. In essence, we are seeing that with just this information, there's still some ambiguity as to which point is which. To settle the matter, we use something called the second partial derivative test, which incorporates all of the information in the table to produce a value which we will denote h. In this video, we'll only discuss the second derivative test for 2 input variable functions. But if you'd like to extend yourself, look up and explore the Hessian matrix. If the value of h is less than 0, we have a saddle point. You can see that this agrees with our table. However, if h is greater than 0, we have either a maxima or a minimum, which can be differentiated based on the sign of x of the derivative of g with respect to x and x. If it is positive, you have a maximum, and if it is negative, you have a minimum. There's a deeper mathematical reason for why this works, but you can think of it as h tells you what the concavity of the function you are analyzing is. Is it up or down, or is it mixed? For the final level, we're adding a twist, an idea we considered briefly before, but we did not explore the significance of. That is, that the majority of things that need optimizing are subject to constraints. Some condition needs to be satisfied for whatever minimum or maximum value we are trying to find. You can imagine a scenario where you're walking on a footpath in a hilly region and want to take a photo at the highest point. You can no longer find the highest point in the hilly region. You are constrained to the path and thus must find the highest point on the path to take your photo. We can mathematically model this situation in order to gain an understanding of what this looks like. A hilly region can be modeled using this rather complicated function, which I would like you to ignore for the most part. Just know that it produces a series of bumps and dips that we can consider analogous to a hilly region. Now on this terrain, there's a straight footpath you can walk on, modeled by the equation y is equal to negative 4x plus 5. The hilly region is an objective function, some multivariable function for which you are trying to optimize, and the path is your constraint. The maximum value on that path would be the solution. We will therefore expand the definition of constraints from linear inequalities used in level 2 to a condition between the input variables defining the set of values where we look for maxima or minima. In the case of our hilly region, we're exclusively looking at the output values for which y is equal to negative 4x plus 5. The orange line showcases the path to which we are constrained. As you can see, the highest point on this path is not the highest point, or the true maxima, of f of xy. The highest point isn't even a stationary point where gradient is equal to 0. This means we need a new method of optimization, which is not dependent on finding points of flat gradient on an objective function. Returning to our hill analogy, we can utilize a contour plot to illustrate the objective function f of xy, and we can plot the constraint function g of xy as well. The blue lines represent different heights of the hill, or outputs of the function. The dark line is the path you're constrained to, modeling the constraint function. At the point where the constraint function is tangent to the objective function, we find the maximum value within the given constraint. The maximum height on the path is the output level of the function that the constraint touches but does not exceed. Thus, the constraint function is tangent to the objective function at that point. This means that the gradient vectors are parallel at this maximum constraint value, which allows us to equate them through some constant parameter lambda. This can also be expressed in vector form, which is worth doing to see how the partial derivatives of each function relate to each other. We can further separate this into two equations, where both equations are made from partial derivatives with respect to x and y individually. As such, we can consider them, both of them, as individual partial derivatives of some greater parent function L. Hence, let's label the first L of x, or the first partial derivative of L with respect to x, and the second similarly as L of y. By reverse engineering these partial derivatives, we can formulate some parent function L, like so. This function is known as a Lagrangian, and the parameter lambda is known as the Lagrangian multiplier. By forming this function, we have effectively converted a constrained optimization problem into an unconstrained problem. We can see that when we find the critical points of L by setting the gradient of L is equal to 0. we get these equations. Lambda is a factor through which we can relate the objective and constraint functions, which allow us to create a singular multivariable function to optimize, which takes into account both the objective and the constraint functions. From equations 1 and 2, once we arrange them, we reach the same statement as we had previously. Thus, just by optimizing this Lagrangian function, the optimal point of the objective function within the constraints can be found. In the exact same way we solve unconstrained optimization problems, we can do this constrained optimization problem. To recap, when solving a multivariable constrained optimization problem, you must have an explicit objective function and constraint function in the terms of the same variables. Use them to form the Lagrangian due to the tangential nature of a constraint at the optimal point of the objective function. Then, by setting the gradient to 0 of this Lagrangian function and solving it like an unconstrained optimization problem, you can find the optimal point given the equality constraint.
We have built an understanding for how functions can be used to model scenarios and be mathematically optimized to find maximum and minimum values. Up till now, all the examples we have seen have been detached from the real world. For example, when we optimized Grug's path, the scenario was heavily idealized. Grug was traveling at a constant speed on a flat path in an uninterrupted straight line. For our final example, however, we will use Lagrangian optimization to solve a genuine engineering problem with real-world constraints. We will minimize the impact force on a falling object in a parachute, where the constraint is the maximum impact force so the object doesn't break. Our test dummy will be an egg, and our goal is to find the ideal mass and surface area of a parachute and an egg to ensure its survival, that is, to ensure the impact force is less than 20 newtons. To make sure we're all on the same page, let's summarize the physics at play. As the egg falls, it experiences gravity downward, causing it to have some initial acceleration. As the egg accelerates, the increased velocity causes an increased rate of collisions with particles in the air. This induces a drag force in the opposite direction. As the speed increases, so does the drag force until both gravity and drag have equal magnitude, thus causing them to cancel out. The egg at this point has no acceleration as there is no net force acting on it, which means it falls at a constant terminal velocity. The introduction of a parachute increases the number of collisions with air particles, thus increasing the drag force experienced by the egg, causing for a slower terminal velocity and thus impact force. Simply speaking, the egg is less likely to go splat. First, let's model a constraint. As a reminder, we are looking for an equation for the impact force in terms of mass and acceleration. Let's start with the terminal velocity, v of t, and let's label this equation 1. The equation for the impact force is as follows from Newton's second law. And by substituting 1 into this equation, we get f m comma a is equal to minus m over delta t times the square root of 2mg over cd rho a. This is our constraint equation, and now we know it takes roughly 20 newtons of force to crack an egg, so we are constrained to where the impact force is less than 20 newtons. Hence, our final constraint equation is the previous expression minus 20 newtons. Now, we can clean this up a bit by considering the following constants. For the drag coefficient, for gravitational acceleration, and for air density rho. And lastly, we are left with f m comma a is equal to negative 30.25 times m times root m over root a minus 20. This is our constraint equation. To define an objective function, it's important to know that mass and surface area are competing quantities. The greater the mass, the greater the force of gravity on the egg. The faster it accelerates, the faster it hits the ground with more force. A large surface area has the opposite effect, as it induces more drag, causing less impact force. We must find the maximum mass and minimum surface area, as having a large enough mass is essential for the egg and its container, and the minimum surface area to avoid unnecessarily large canopy, which would itself have a substantial increase in mass. To balance this trade-off, we can use a balancing coefficient mu. Gm, a is equal to mu m minus a. If mu equals 2, then we are prioritizing the effect of mass on the outcome of the equation. Now this is a technique known as prioritization, and it allows us to favor some variables compared to others. Now, we can perform Lagrangian optimization by first forming the Lagrangian function and substituting in the constraint and objective function defined. If we then perform the first partial derivative test as previously taught, we can equate the gradient equal to the zero vector and thus set all of the partial derivatives to 0, allowing us to solve 3 simultaneous equations. After solving, this leaves us with mass as 0.664 kilograms and area as 0.669 meters squared. This means our maximum mass is 0.664 kilograms while our minimum surface area is 0.669 meters squared. To check this, we can substitute these values back into the equation for impact force as follows. Doing so leaves us with 19.998 newtons, roughly equal to 20 newtons, which shows us that this approach has correctly optimized the mass and surface area to allow for an impact force that ensures the egg doesn't break on impact. Hopefully now, you appreciate the beauty behind optimization, with the new understanding of how to apply it to real-world situations. Optimization is a mathematical topic that once you start learning about it, you see just how deep the rabbit hole goes. And while it may get more mathematically challenging, all optimization problems can be broken down to the same simple principles. This simplicity allows for elegant geometrical analogies like we saw in the Lagrangian optimization section. With that being said, we encourage you to use these techniques to come up with and solve your own constrained optimization problem that interests you. The most valuable thing you can ever learn is the ability to do something for yourself. So in forming a problem and solving it to find the optimal solution, you will gain a truly valuable skill from this video. Thank you very much for watching.